Okay, thank you, Amanda. Well, so I'm going to talk about an interesting physics question of how currents, plasma currents, close on the surface of a non-conductive plasma-absorbing body, and the insights that we've gained from two Cassini flybys of Rhea from Cassini IMS and the magnetometer. So this is the arrangement of the flybys. They both flew, so this is looking down onto Rhea. The plasma flow is from top to bottom, and the flybys flew over the northern and southern hemispheres of Rhea through the Flux tube. And so you can see here, this is again an equatorial view of the flybys going over the north and the south, and these dashed lines here indicate the Flux tube. So there are two measurements of relevance here. One is the measurements of the density of the exosphere of Rhea from Cassini IMS, and you can see that we detect during both flybys exospheres of oxygen and carbon dioxide. There's a little bit more over the north and over the south. That has to do with the seasonal effect in the exosphere. But densities of the order of 10 to the 10 molecules per cubic meter. And I just show here for comparison the Dione results as well. We see an exosphere of similar composition and density there. But in addition to that result, now you can see that I've indicated by the O and the X the directions of the perturbations in the magnetic field that we see as we fly through the flux tube. And there's a jump going into the screen here, or out of the screen and then into the screen, and then in the reverse direction on the opposite hemisphere. And so here are the results here. And you can see that first of all, let's look at the BZ component. You see that the magnitude of the magnetic field increases as we get close to Rhea. This is expected since you have a plasma absorbing body, and the strength of the magnetic field is being enhanced to compensate the absorption of plasma pressure by the body. But this here is unusual. These perturbations, especially in the X and a little bit in the Y direction, orthogonal to the direction of the ambient magnetic field. And that is reminiscent, for example, of an atmosphere, of a conduction current through an atmosphere, or perhaps a pickup ions being created by the atmosphere. You would expect to see these orthogonal perturbations. And you have something similar here during the R3 flyby. This sharp peak in the X direction, it reverses direction, and then it recovers as we exit the flux tube. But the major problem here is that the density of the atmosphere, if you do the calculation of the conductance of the atmosphere, as seen at the density that we observe by IMS, it's roughly 2 orders of magnitude too low to produce sufficient currents in the system to account for these field perturbations. So you have a puzzling question here of how is it that you can produce something like this when you don't have enough atmosphere to do it. So this is from the Sven-Simon paper in 2012. He's done a nice job here of applying a hybrid model to the Rhea plasma interaction. And you can see his fit to the R3 data. It's not bad. The hybrid code gets the rounded part in the BX, and the BY and BZ look pretty good. R2, the fit is not as good, but you get a drop here, and it looks somewhat similar, but you can see right away that the major problem here is that these simulations do not succeed to fit these sharp features at the edge of the flux tube. So the red is the fit, and the Simon et al. Explains it in terms of currents closing across the wake, the downstream wake. So you have a diamagnetic current, closes across the downstream wake, produces a BX perturbation, and that can produce an Alfvén wing, which is seen, may see some signature of that in the flux tube. But the story is somehow incomplete, because you can see that you have these sharp perturbations on the edge of the flux tube, and they happen during both flybys. So something's going on there. So that was the question that I was looking into, to see if there's some way, is there something wrong with the hybrid model, or is something that we're not including there that could explain that. And it turns out that the issue has to do with the execution of your standard hybrid model. These are the elements of the physics that go into the hybrid model. So you have force balance for the electrons. The ions are treated as particles. and Faraday's law, Ampere's law. To make a long story short, you can solve these things and generate a magnetic diffusion equation. And that equation is solved in the hybrid model to determine, and this thing is iterated until you reach a steady state or something close to steady state to determine the configuration of the magnetic field. But you can see the problem here because something, unlike an object, for example, with an atmosphere around it, this is a non-conductor, so it's got a high resistivity, and it has a sharp surface. And this presents a problem for a differential expression such as this, because if you expand the terms here, you can see that we have terms which are proportional to resistivity and the gradient of the resistivity. And the gradient here is a Dirac delta function. It's a sharply peaked thing. And that presents a problem, a numerical problem, for evaluating this thing over a finite mesh in a computation. So the best you can do really is to model something like this. You have to smooth the object such that you can circumvent these numerical problems and hope for the best. So with the idea in mind that maybe perhaps this could be the problem, I wanted to see if there was a way to solve the physics such that we could simulate an object like this. And it turns out it is possible. You take the same physics, the same elements of the physics, and you solve the equations in a little bit of a different order, and you can reconstruct the differential expression in the form of integral equations. So you have force balance here. I solve for the perpendicular electron currents algebraically. Those can be then integrated along the field lines, and using current continuity, the parallel electron currents can be evaluated. That then leads to the electric field. That's iterated into the calculation of the magnetic field, which is done this way, and round you go until this system reaches a steady state. You'll notice here also that unlike the expression here, which is a time-dependent expression, there's no time dependence here because all we're after is the steady state. So this is a little bit of a different strategy. Instead of evaluating the temporal evolution, solving the temporal evolution and allowing that to relax, here you bypass the temporal evolution and you go directly to the steady state. And provided that you can solve for the currents which satisfy these conditions, that can go directly into the Biot-Savart law for the magnetic field, and you get the magnetic field everywhere in the space, including inside the body where the resistivity is high. So you avoid these issues, for example, of having high magnetic diffusivity inside the body. This thing will solve for the steady state magnetic field outside the body, inside the body. So it solves a number of problems here. And I give more details in the recently published paper here if you guys are interested to see how that works. So the question is, does that work? Well, I implemented this procedure in the computer, and just to do a sanity check first. So this is the differential hybrid model, and this is my model here with a blurred Rhea profile to try and approximate what you get in the differential case. And this is just to show that in those two cases, both models agree. But now we have the ability in the integral version to put the sharp object in, and you can see that you now match the peaks at both sides of the flux tube and this notch in the middle, and I'll explain that in a minute. And this is the R3 flyby as well. Same thing, a blurred resistivity profile. This is the density of the plasma, by the way, and I'll get back to that issue in a second. But this is the blurred profile, and then when I sharpen the object, again, you can match the peaks at the edge of the flux tube. The shape in the middle of the BX is a little bit off. It's more rounded in the data. So, but if I raise the density, which is consistent with RPWS measurements of the density was higher at R3 than it was at R2. When I make that change to the model, I can also reproduce this broad shape in the middle, and I'll explain what that means and why that happens in a minute. So first of all, what's going on here with these peaks? Well, now that we're able to fit this, we have the ability to look into the model and see what is the physics of that, what's responsible for that. And it's basically this. You have the simulation, now that it's working with a sharply defined object, it has to balance currents on the surface, on the sharp surface of the object. So The ions are absorbing, they have a large gyroradius, so they absorb from roughly all directions into the surface. And to maintain steady state on the surface, steady state surface charge, you have to draw in an equal number of electrons. Well, the electrons have a much smaller gyroradius, they're tied to the magnetic field lines. So they move into the surface like so to equalize the ion currents on the surface, and this difference here creates a current system which moves in towards the equator and out along the edges of the flux tube. You'll see also that the current is more intense on the edge of the flux tube than it is in the center, and that's responsible for the R2 flyby, for the fact that the profile was notched in the middle. This shape here. So there's more current on the edge of the flux tube than in the center, and that's what's going on there. And this is just to show why you do not get this same current system when you have a blurred object. What basically happens, this is somewhat of an oversimplification, but it's essentially this, that when you put the blurred resistivity layer around the surface, it breaks the circuit and kills the current. So you don't get these features unless you have a sharply defined object. So you need a code which is capable of doing that. So there's the current system. Again, the blue is currents flowing south, the red is flowing north. So this is the results of the simulation. You can see the diamagnetic current spirals into the equator and goes out along the flux tube. And this is what you see in the magnetic field. So you get this Alfvén wing from the wake, and this is the Simon et al. Mechanism that you're seeing here. Wake currents closing across the wake as the wake fills in, as plasma diffuses into the wake, produces this feature, but then you also get this flux tube helix due to the flux tube current. And now this current system has some interesting features. For one, it doesn't require motion through the plasma. So, for example, if I turn off the flow of the plasma in the simulation, the Alfvén wing goes away, but the flux tube current system is maintained. So this current system is driven kinetically by heat flow, essentially heat flow from the plasma into the object. Ions are driven into the object just due to their thermal energy, and that drives a current system along the flux tube. So motion of the plasma past the body is not required to maintain this current system. And you can see also here, so this is the current system, and the color is the BX perturbation on the plane here. So that's the component of the magnetic field that is pointed in the direction of the flow. You can see here the signature of the flux tube current and the Alfvén wing here. And now watch what happens when I increase the density of the plasma. The Alfvén wing moves back toward the body, and the reason is that as the density is increasing, the ion inertial length is decreasing, and the plasma itself is now able to respond to the fact that you have a flux tube current. It starts to see that as an obstacle to the flow, and the flux tube current itself creates its own Alfvén wings. So this Alfvén wing coming from the wake starts to get replaced by a second Alfvén wing, if you like, coming from the flux tube current itself. That produces an additional BX component, and that's what you're seeing in that R3 flyby, as the density of the plasma increases. So there's the Alfvén wing, and this is if I increase the density further, you can see that the Alfvén speed is decreasing and the angle is going down. So just to get to a conclusion here, you can start to construct a general picture of the interaction of plasma absorbers generally. So this should occur at Rhea, but this physics also applies at other objects in the solar system as well. So you have a flux tube current with no motion through the plasma. You turn on the motion and you get a diamagnetic current in the wake, start to increase the density, and this creates an Alfvén wing from the wake, and if you increase it further, additional Alfvén wings are created from the flux tube current itself. So a number of interesting findings here, and just with these two flybys and multiple instrumentation measurements from the magnetometer and the INMS, we're able to compare and contrast those things and learn quite a lot about the physics of these plasma-absorbing bodies and how they interact generally with plasmas. So thank you.
We have time for just one quick question. And if you could use the mic, that would be great, because it's streaming. The idea with the absorption is very interesting, but you pointed out that you treat like the sharpness of the conductivity discontinuity at the surface correctly with the new integration model, but it's steady state. And I'd like to point out, we developed a time-dependent solution to this problem. It's published in Dueling et al. This year, and it's download. In the supplement, it's the subroutine to download, so you could even use it in the time-dependent case, like the full resistivity inside and zero resistivity outside.
Excellent. That's a great point, and it's certainly possible to formulate these things in time-dependent terms. And I'll take a look at the reference that you just cite there. So thank you.